Okay, this is Screencast 7. Question 1 says, two people pushed in the opposite direction on a crate sitting in a frictionless surface. The crate is initially at rest at point A, then moves left without rotating, and ends up at point B. Describe how much work is done by each person. So I drew up my free body diagram. There is my box, which obviously has weight and normal force on it. We have person 1 pushing this way, and then person 2 pushing this way. We have our x and our y coordinate to set up, so we know that one person is pushing in the positive direction, one person is pushing in the negative direction. We also know that it goes from point A to point B, and it's at rest at point A, then it's at rest at point B, which is going to equal to 0 kinetic energy there. We're going to use the work energy theorem to kind of help understand this, to see how much work is done by each person. We know that the work energy theorem, we know that total work equals the change in kinetic energy. We also know that it could be written also in the 1/2 mass velocity final squared, 1/2 mass velocity initial squared. We don't know the velocity, we don't know the mass, we don't know any of the above, but the one thing that we know and that we should consider is that it's at rest at point A and it's at rest at point B, which that equals 0 kinetic energy. So the change in kinetic energy is the kinetic final minus the kinetic initial, which in this case equals 0. So the total work done in this example is 0. So we know that there's work done in this way that we could call negative, and this work done this way, which we could call positive, by the two people. So the total work is the sum of works anyway. So we just did that. Net work equals 0, which equals work 1 minus work 2. And then if you put work on the other side, W1 equals W2. Therefore, the work done by each person is going to be the same. Okay. This is wrong one. Brimstone. Okay. So in this question, it asks us, suppose you're climbing a rope that is hanging freely from the ceiling of a gym. The rope does not stretch as you climb it. If you climb to a height h, how much work has been done on you by gravity, and how much work has been done on you by the rope? So we need to know the work on you by gravity and the work on you by the rope. We have a free body diagram. We have the mass, which is the person, which has weight and normal force going up. It obviously has velocity going up. I just drew that in there so I could think about that. There's a height, which will be y1 and y2 has a initial and a final. And we could go up the positive direction. What we know is that there's an mg, there's gravity, which is going to be negative in the final thing, because we're going in the opposite direction of gravity. Gravity is pulling down, object is going up, so the gravity is going to be negative. And we know we have height. So the total work done on the person by gravity is going to be work negative mgh, just because the work done on the person is going to be negative. And I explained why. So that's going to be the total work done on the person by gravity. It's going to be work equals negative mgh. And if you knew those subscripts, you'd be able to plug it in. Now the work done on the rope is going to be on the rope. It's basically going to be the same thing, just not negative, but in the positive direction. Although I took a little bit more time thinking about this, going step by step for it. We know the work equals force times distance. We know the work also equals force times distance cosine angle. In this case, cosine angle is 0, so that would be 0, so which would also equal force times distance again. But in this case, object is going up the rope, so the work would equal mgh, but it would be positive. Instead of here, it was mgh negative.